So let's welcome our next speaker, Professor Ima. Professor Ima is currently at UC Berkeley, and I know that previously he was also associate professor at UIUC from 2000 to 2011, and also the principal researcher of Microsoft Research Asia from 2009 to 2013. So he was then the founding professor and the executive dean at Shanghai Tech University from 2014 to 2017. And now he came back to UC Berkeley where he obtained his PhD. Okay, yeah, so let's welcome Ima from talking about his interesting talk about 3D parsing. Yeah. Probably you're muted. Yeah.
Can you hear me now?
Yeah, yeah. Mm-hmm.
Yeah, let me share my screen. Just let me know if you can see my screen.
Yeah.
Yeah, I'll try to make the switch to the full screen. Yeah, thanks for having me. It was very exciting workshop and listen to all the good talks. What's happening to my, okay, can you see the full screen now?
Yeah.
Okay, good. All right, this is a work about, as you can see the title, how to, using sort of back to the fundamentals now, right? How do we detect 3D geometry? How to really understand 3D, get a 3D reconstruction? So this is a topic has been very classic, right? Probably everybody in this workshop should know, right? The history, probably 30 years or 40 years of practice. It's kind of interesting. This source, I started with this with my PhD study. It's surprising to see after about nearly 30 years, the practice has not really changed much, right? I'll give you an example. I just joined Berkeley about 3 years ago, and one of the first talk I heard at our AR/VR seminar was the CTO from Magic Leap. This is exactly the same kind of pipeline, right? How do we reconstruct the 3D environment from extracting certain local features, shift and the warps, whatever you have, and establish correspondence, use the multi-view geometry, bundle adjustment, or SLAMs to get a point cloud representation of the 3D room or environment, right? Till this day, nothing has changed, right? It's just basically engineers getting better and better. When I actually heard that talk 3 years ago, I talked to my colleague. I was really worried about the future of Magic Leap because this is exactly what I have been doing at Microsoft for 5 years, right? We're engineering exactly the same pipeline. We know exactly when they work and when they don't work. There's no way, based on that kind of systems, you will be able to enable the kind of diverse environment that AR/VR, future AR/VR is supposed to work. For example, in a situation, man-made environment, there's not much features, or there's reflections, or there's repetitive patterns, or baselines gets a little bit larger. And actually, in the VR applications, very often there's a dynamic object in front of each other. We all know this classical pipeline has all the problems with these issues. In fact, right, it's kind of ironic, right? Our brain, we actually recover 3D shapes much better in this kind of man-made environment, right, than the kind of techniques that enable that a classical structure from motion would work. This actually always baffles me, right? For example, this repetitive pattern, right, the rail. This would never, however sparse structure from motion or SLAM system you have, try out this kind of scenario. See if they succeed. Right? They fail miserably, all of them. But the people don't show you, right? This is the days people publish papers, they never show you the failure cases until they publish the next paper. So this is, of course, a few years ago, right? This is what people in structure from motion geometry has been practicing for many, many years, try to make it more robust and accurate. But then, of course, a few years back, about 10 years back, people started, deep learning started to become very, very popular, right? People started to propose that maybe you can use a learning-based approach, right? Indeed, in many cases, that the learning seems to be more robust in some cases, right? For example, as composes even for a single view image, the depth, voxels, mesh, and so on and so forth. So it's many applications being proposed, right? They have seen a lot of success. However, if we are serious about certain applications, for example, AR/VR, you really care about accuracy, right? Millimeter, centimeter accuracy, millimeter accuracy. let's just check, right, how well they're doing in this kind of scenario. This is a study, right? After many papers published, this is about a couple of years ago, people do some serious evaluation of all the learning-based approach in the recovered geometry, surface, and so on and so forth. It turns out, right, at least for many of the straightforward approach using deep networks to do 3D reconstruction, right, the performance actually is not even as good as if you do a very serious nearest neighbor. Right? Basically, the network is really trying to remember all the instances. They're really doing a query for you for the database you use it for training. And this is also bring us back, right? So the geometry-based approach has developed in the structural from motion and so on, so for using features, and also learning-based approaches trying to, using all the input-output data, try to use leverage learning, right? But if you look at how our human being be able to recover structure, it's actually, we don't necessarily need that many images, right? So there's very rich information in the scene, in the image, and we barely use them for 3D reconstruction, especially in the classical setting, right? There's the lines, parallel lines, smooth curve, parallelism, orthogonality, symmetry, and so on and so forth. From a single view, we almost have a perfect perception of 3D geometry, right? Which means there's tremendous information there. They're not encoded in local features, not on the shift, not on the corners, right? So how can we actually leverage those? But not just to guess what might be the surface normals are up to certain degrees, right? 10, 20 degrees, we'll be happy, looks good. No, we wanted to get accurate reconstruction of the scene. In fact, if you think about it, right? So after 30 years, we still practice using local features, right? Shift and so on, so forth, so orbs and so on. But the understanding of the global geometry has been there forever, right? So about 20 years ago, we understand the multi-view geometry of not just points, junctions, but also lines, planes. Actually, in all incidence relationships among all the lines, planes, and also symmetries, all types of symmetric object. And I think about the former the talks also mentioned that those are very important for global understanding of the scene. But barely many of them has been really used, or we don't even know how to use them for 3D reconstruction purposes. I mean, today we'll try to go through a few things. Now the question is that we understand the geometric relationship, but the question is how can that get encoded in the learning approach? We actually see the early practice of deep learning for 3D vision. Right? Without taking into account those geometric constraints, geometric information, actually they're not that better than nearest neighbor, just doing data retrieval. How can we do better, right? So today I'll go through a few sort of vignettes, right? We actually gone through in the past few years, a few papers, right? We actually started to go back to the very basics. How can we actually produce and provide more reliable information to the geometric inferences, 3D reconstruction, from junctions, lines, planes, and also even symmetry and so on and so forth, right? Combined with geometry and the learning, right? You can see that we'll start with our early practice attempt to try to recover from larger global structures such as junctions, lines, and also how do we get the line detection and even vanishing points. Surprisingly, many of you guys may be laughing. This is such a simple problem, right? In the modern age of deep learning. Well, think twice. Even in this simplest, most naive 3D reconstruction problem, actually learning doesn't really work that well, right? Let alone with symmetries. We start with this. So this is our early attempt to try to understand how we can integrate learning with geometry, right? This is ICCV 2017 paper. How can we go from an individual image, a single image, back to some kind of CAD representation? Like our human eye is able to do that, do this high-level inferences. Of course, what you can see is that you can train, using the deep networks to train, let's say, estimated line segments, also some of the junctions. As I say, I'll skip some of the details, but just give you the basic idea. And then once you have those components, junctions and the lines and so on and so forth, and also the vanishing points, and you should be able to combine that, solving an optimization problem, combine the geometric relationships, and just solve a, you can relax it as a complex optimization and to get the 3D model. Okay. So this is the results, right? From a single image, at least conceptually, this paper verifies it's possible, right? And if you can reliably detect those ingredients, junctions, lines, and also their relationships, and you should be able to do this kind of inferences. And actually, this is more. This is a trend on the synthetic data set and about 10 blocks of city. And you actually can see that with ground truth and inverse 3D, just like any other papers. But we will show you, this is, how to get a published paper, you show the successful examples, right? Well, those are the failure cases, right? So we know that, that when you get this line detection itself is very, very challenging, especially when they get short and dense. And also, by the way, actually, even the vanishing points, such a simple 3 vanishing points detection problem, as of 2 years ago, it's not even solved, right? Nothing worked. At least not as reliable, as accurate as we hoped for. So we'll go through that. So that actually forced us to go back to think about how can we actually further improve the line detection. Let's see, right? So for example, this is what a very classical problem, right? Many of you probably played with edge detection, but this is more global, detecting line segments, right? Have straight lines to ending points and so on and so forth. Right? You can think about it. This is a kind of you can say this is kind of simple object detection problem. Actually, it's not quite, right? You can see that why? Because although the appearance of edges looks simple, but actually they can be of all orientations, and the number of them can be massive, and they can be very close to each other, and the support can be very, very different, and they overlap with each other, right? This is really not a classical like you can easily solve with mask RNN. Actually, mask RNN actually doesn't work very, very well at all here. So the question you really have to resort to how do we combine the learning and also the geometry of the lines in a very clever way. So this is one of the attempt. Again, we try to use the leverage object detection, but here we're detecting very specific class objects, right? We know they have very, very geometric interpretations and parameterizations. We're combining with detection with a line parameterization, and you can train a sort of end-to-end networks to do this. You can see that this actually started to become a sort of promising, right? This is the old classical line segment detection. This is sort of based on edge detection and the line segment fitting, right? You can see it's very over parameterized and over fitting the scene, and also the lines are broken. There's nothing really global, and there's afterwards, right? While this is the first attempt of a wireframe, and then with a more better geometry and aware of learning framework. Actually, you can see that the performance started to get very, very good, right? So you can see actually even the computers can detect lines that even human forget to or fail to mark, right? So this is kind of a very interesting, and also you see that even here, right? Those are the some of the lines are being harder for human to perceive, but actually with a well-trained system, you can actually be able to detect the countertop of the chair. And you can see that once you combine, right, this is some of the earlier attempts, just basically purely still very brute force learning based approach, but it really combined with a good geometric modeling. You can see the jump from the just purely learning based approach, treat this as a more generic detection problem. It's humongous, right? So this is actually very quite surprising to us as well, right? And there's still actually room to improve, by the way. It's not just some of the recent work. Not only you are actually to improve the accuracy, but also improve the speed. This is we can run this in at 50 frames per second and so on and so forth. So that's actually about line segmentation, right? But lines have relationships. They're not independent, right? We know all the lines, for example, in the memory environment, they're all parallel, right? So how can we, all the parallel lines converge at the vanishing points, right? They're very, very important, by the way, right? Especially in the memory environment to give you the orientation, right? People can build visual compacts. It's very important for SLAMs and so on. So now, and also this sounds like a very, very simple problem, right, for detection. So parallel lines intersecting at an individual point, and actually in most of the cases, you may only have a few set of parallel lines, which means that there are only 3 or 4 maximum vanishing points. But how can we detect them sort of reliably? And also, this is a slightly different, although they look simple, right? But it's actually this is actually very different from traditional object detection. Why? There's really no image of vanishing points, right? They're actually something abstract. They're the relationships of parallel lines in the perspective projection. So of course, there's 2 approaches again, right? People do traditional approach, edge detection and clustering, half transform, ransack, and so on and so forth, line fitting. You get this. If they work, that's actually pretty accurate. But over the pipeline can break down, right? You get a lot of false positive negatives. The same thing, people also tried the neural networks before us, right? It's to end-to-end training neural networks. They're actually pretty robust. Most of the things they can guess reasonably well where the vanishing points are, but it's incredibly not accurate, right? Especially if you use those for AR/VR accuracy, you want the accuracy to be, let's say, to a simple, this is a typical characteristic, right? So if you want the accuracy to be within, let's say, 1 degree, right? You can see the traditional approaches, right? Up to 50% or even 80%, the accuracy is pretty good within a couple of degrees accuracy, but they're actually not that robust, right? The yellow curve is the learning-based approach, right? It's not very accurate, but if you're only okay with within 10 degree of error, I mean, they're actually successful almost all the time, right? So they do very good guess, but they don't expect them to be any accurate, right? So this is actually the really where in this dilemma, right? If you use traditional geometric based, they're very accurate if they work, but very often they fail. Another question is, how can you combine both, right? So traditionally, that people, look at the right figure, right? People do convolution neural network, but it turns out in the detection of vanishing points, you're detecting edges of a parallel lines, right? A set of parallel lines. Hence, the orientation of the line actually correlated. You should not just use a generic convolution. You should actually, based on the possible location of the vanishing point, you should adjust the filter, even these edge filters as well. So this is what we did, right? By actually encoding this tiny little bit about the information that the network is supposed to be aware of what kind of object they're, how they're correlated spatially. And then you actually replace the classical convolution with we call the conic convolution, parameterized by the vanishing points. Then you actually can see the performance suddenly jumps incredibly, right? You start to really enjoy not just the accuracy of the traditional approach, but also the robustness of learning-based approach. In fact, on this large city synthetic data sets, in fact, the method actually achieved nearly the numerical accuracy that achievable by the resolution of the image, which is very, very surprising, right? And even on real images, you can start to see, right? This is a classical and also the learning-based. Actually, you get much better combination of both. You enjoy both of the, and you can further improve, make this much, much faster, and you get a very reliable vanishing point detection. You can apply the same thing to surface normal, right? Rather than treating your scene as a generic surface, but actually they're highly structured. They're mutually orthogonal, parallel, and so on and so forth, right? So you can get a much, much more accurate surface normal for learning-based approach. Now, that's actually just the lines, right? And also relationship from one lines. And also, I just like some of the former talked about, right? Objects, the man-made object has all kinds of structures, right? And how can we utilize that, right? They're not just a point clouds. They're not a generic mesh, right? For example, many of the autonomous driving, we try to detect the object, the orientation, location, and so forth. Questions can we actually get from single or multiple views? The same thing. One thing you realize, right? At least the symmetry is actually not that different from vanishing points, right? So, but they're, in the edge detection, in the vanishing points, those edges are visible. Here, with the symmetry, those edges are not visible, or at least most of them, but they exist, mathematically, right? The question is, if you can actually, detecting the reflected symmetry is precisely mathematically equivalent to actually detecting the vanishing directions, the reflection angles. So be aware of it. Hence, the image, a single image like this is actually equivalent to 2 images, right? You're actually, this is actually equivalent to looking at the chair from both left and right. The question, how do you incorporate that into the learning, into the computation, right? So here is again, when you try to learn the shape from learning, right? So you actually try to encode the object you're looking at, likely have a symmetry, bilateral symmetry. Right. Hence, the voxel, whatever you are regressing, right? Your deep network try to regress the cost volume. Actually, make sure that cost volume respects the geometry. Right? Encode that geometry, the symmetry within the cost volume. Right? That's all there is. Right? Details in the paper. It's actually once you realize, you just enforce the structure of the network to respect the symmetry, likely symmetry of the object. Once you do that, you can see again. You see the same phenomena, guys. Right? It's not just the incremental 2%, 3%. It just start to work, right? Start from the accuracy from this is from the previous work. You start at 50%, 90%, right? The accuracy and also success rate. Right? In fact, this is showing that once you did compare with the ground truth, detected the symmetry as well as the reconstructed depth. The accuracy and so on. Right. This is also, I think, one of the Europe's paper this year. So this is actually I showed you a few examples, right? Indeed, for 3D reconstruction, especially in the memory environment, if we strive for robustness and accuracy, we have to start to utilize large-scale, much more information-rich structures. Okay, you can still use SLAMs or for local features, but they're not going to solve the problem. You know, whatever has been solved is solved there, right? But what they cannot solve the same scenario, they cannot solve. You really have to strive for larger holistic structures and their relationships. They're much more accurate. They'll give you much more accurate and robust reconstruction results. Right? But don't forget, all these techniques are actually one thing, right? We showed you, right? They're all depends on the data. It needs to be trained. Although those networks are designed, are aware of the geometric structure, but they still needs a lot of data to train the networks properly, right? So one thing we actually, once we started this project, we start to realize that probably, you know, maybe in the human study, human body work has shared the same difficulty, is that you do not have 3D ground truth, right? Unlike, you know, in 2D images, you know, segments, and also you have lots of annotated 2D images and objects and also segments and class labels. But for 3D vision, there's really tremendous lack of high quality, massive, large scale, realistic 3D data. We have a lot of synthetic data. That's also many of the work you see actually conducted on the synthesized data. But for realistic data, we're really short, right? Especially annotated. So we're actually almost forced to, this is one thing I sort of cry for the industry to help, right? So in the academics, we're very, very, you know, limited by our resource, but we tried anyway because we couldn't really wait. Right? This is also the first time we actually work with some of the companies to try to, you know, can we build really the city level scales data set. This is what we call the holy city. It's a sort of try to sort of using label the street view images from Google, and also with working with a company which has an entire CAD model, very detailed CAD model for the downtown London, right? So this is actually really that what we found out, right? So despite we have all those components, but in order to really to carry them out to the real world, you really have to get them trained, right? The networks trained on those realistic data and the realistic scene, right? So hence that you can think about this days, everybody think about AI is about coding, but actually it turns out coding is a very tiny detail of that effort, right? The rest of it is really just trying to get your training data ready. But this is actually very rich data sets. My, you know, Yi Cao, actually, my former PhD student, spent about a year to develop this network, this data sets, right? So, you know, has all kinds of annotations and CAD models with the semantic, not very dense, but actually most of the important categories are labeled. But the image quality is very high from the high quality street view panorama image from Google, right? So it actually covers quite big, right? It's like 20 kilometers square of the environment of downtown London, and it really actually can support all kinds of 3D surface normal, plane, lines, junctions, and also that even semantic level or CAD level, CAD model level inferences. Right, this will give you a little bit idea. Now, of course, we don't solve the problem yet, but we can benchmark, right? One thing we found out, to be honest, right, as soon as we start to apply many of the wonderful work on 3D learning-based 3D reconstruction, surface normal on this realistic data set, actually the performance is pretty, you know, moderate, yeah, to say the least, right? I mean, basically they do not generalize whatsoever. Okay, pretty bad. So the question really is what it takes for us to really combine geometry and also learning-based approach for this kind of get a very accurate, reliable, large-scale 3D reconstruction and mapping, right? That's completely unsolved problem. Fine, if you use a lot of laser points or structure from motion using dense set of images to get a map point clouds, you may be able to engineer one. But as far as high-level 3D mapping, understanding, precise, accurate, robust localization and reconstruction, this is far from solved. And hopefully this data set start to help us to understand how far our journey is yet to be. So that's basically, I want to summarize last couple of minutes, right? So the question really is, how do we you really cannot solve 3D reconstruction, 3D vision, even as basic as recover 3D maps, let alone all this, dynamic human motion and also dynamics and so on, right? Even the basic classical problem, map 3D environment, with to achieve a higher level representation of the scene, right? We need to combine geometric-based method and learning-based method together. Always strive for one of them. It's all only can solve limited problems, right? And here's just sort of, give you a sort of overview of summarize, we need very good data. We need a very good data. And so this is actually our journey in the past few years, last 3 years, while my student tells very much his thesis, right? Started really kind of investigating how the learning-based approach would helps us to get the help with 3D reconstruction and providing really deviate or incorporate the recognition into the reconstruction pipeline, rather than really still engineering the traditional point clouds and so on and so forth, right? There's a few publications listed here. And there's also a couple of workshops. I think a lot of structure for motion folks start to realize then we really have to incorporate structure reconstruction and also to have pipeline be able to utilize the holistic structures and their relationships rather than using generic point clouds and a mesh. Right. Yeah, that's all for today. Yeah, thank you. I can take some questions. Maybe.
Yeah, that's a great talk. Yeah, there's a question in the chat box. So from Yuliang Guo. So the question is, would it require higher complexity in the matching process when using the structure elements? How do you think the structure representation can better help the action, for example, navigation and manipulation?
So so far you can see that we're very back to the ground, scratch, right? So just imagine that so far most of the work I talked about today, except probably the symmetry requires the pairwise view. All the other work is still single view based. We're still trying to detect the elements, right? Just like almost that you try to extract the shift features from individual images, right? And yet with the higher level structure like lines, junctions, and the planes, and also the symmetry, they already allows you to get a 3D reconstruction, but they are definitely not enough. Okay, that's said that one. Then what your question is about how this would, if you have a multi-views, right, stereos or sequences, that's actually also something we're precisely working on. Conceptually, of course, the matching will be much less ambiguous if you are able to detect those large scale structure more reliably, right? They have much larger support, they satisfy more strong geometric constraints. So the matching should be much more robust. And actually our early results indicating that too, right? But how to precisely do that most efficiently, most accurately, how far we can improve over the traditional pipeline, we're still working on that. Right? But that's also the reason why we want to go through the holistic structures, because they make the matching and the loop closure and a lot of problems much easier, at least conceptually. And also now, your second question is that the reason for this is precisely for AR, VR, right? The representation of 3D, right? Honestly, a point cloud is really not a good representation for AR, VR, right? I mean, average Joe do not interact with. I mean, those data are very, very expensive to compute. Not just point cloud, mesh is the same problem, right? It's very data intensive and very intuitive, counterintuitive to interact with, and at least not for experts. Right? So the question is, how can we actually move beyond that to get a much more high-level geometric representation in terms of wireframes or CAD level representation, or even semantic level representations that provide not just the semantically meaningful, but also accurate. I'm talking about accuracy, right? Millimeter accuracy models that allows people to interact, right? To render, to editing, right? So this is actually, we're actually moving on. And one thing about this high level geometry is that they actually allows you to not only provide a user-centric localization, but actually start to do object-centric, right? In neuroscience, it's called egocentric or allocentric representations, right? So those actually, for example, symmetry or vanishing points, they're all allocentric informations. You actually can represent how your viewpoint relative to a certain object, right? Rather than having the whole world represented as a point cloud relative to you. So this is actually a few things really allows you better human-machine interactions, right, for the future or in a VR AR situation. So those, I hope that is also some of the motivation precisely why we believe we have to move beyond the point clouds and really working with structured geometric representation. Thanks.
Yeah, thank you. Yeah, this kind of structured representation is pretty interesting. And there's a brief, small question about, you briefly mentioned homography or convolutions for estimating the planes. Is that an ongoing work? And I think
yes.
Okay.
Yeah, actually, that's some of the Yi's ongoing work. Basically, apply the same. Basically, the point is very, very simple, right? Traditionally, people do plane estimation. Again, it's very data-driven, learning-based. But turns out those planes in the memory environment, they're not IID, they're not random, right? Their orientation are highly correlated with each other, parallel, orthogonal, and so on and so forth. And just with that prior encoded in your learning framework, you can show that it can tremendously not just improve the speed, but also improve the accuracy of those planes much, much higher. And also those planes are not just surface normal, local patches, but they're formed by parallel lines, right? A rectangle lines. Those are all information, what we call the incidence relationships, right? So far, actually learning has not really been able to utilize those highly, mutual constraining relationships, right? Line intersecting points, lines that share the same plane, the planes are orthogonal, lines are parallel and orthogonal, right? How those informations can be systematically utilized in the inference, data-driven inference approach, right? To help you to learn a better inference. That's actually, I think, one of the most intriguing problem in this setting.
Yeah, thanks. I'm looking forward to future work. Yeah, okay. Yeah. So if the audience have further questions, feel free to use the chat box to post a question. And if Professor Ima, you're free, then you can feel free to use the chat box to reply to them. Yeah, okay.
Sure. Yeah.
Yeah, thank you.